So the very first step will consist in using BayesiaLab in order to load the data. So it's a survey data. As we said, it's made of 1,321 rows, so one line per woman. And then we will use this data import wizard in order to define the format of the data set, to associate type to each variable, to eventually probably use missing values, processing, and then define the discretization. And after this this step, we will end up with our first Bayesian network that will be a fully unconnected network, where we will have one node per column, and everything is unconnected. And then we will have to find what are the relationship between these variables. Then the second step, once we have this unconnected network, is to find what are, you know, if you remember in the Stefan presentation, he was talking about the relationship between the x's. And so here the idea is to first build what we can call a ground network. So we will first exclude the target, the purchase intent, and only work on the x's variables in order to find what are the relationships that hold between these manifest variables. And we will end up with this kind of graph, so where we have directly all the relationship between these x's. And then the third step will consist in analyzing this graph and trying to build a concept. So we will do what we call variable clustering, and again within the same framework, using Bayesian network and not factor analysis, we will be able to directly identify groups of variables that share common characteristics, and that can then be grouped into one cluster, into one factor. And once we have done that, so the fourth step will consist in building, really inducing a new variable, so creating a new row in the data set in order to summarize the manifest variable into one higher level variable, if you will. And then, so for each identified group, we will build a small Bayesian network with a new variable that will summarize these five, in this example, 5 manifest variables. And then at the end of this multiple clustering, we will end up with 15 new variables. So we had 49 variables, manifest variable, and then after this processing, we end up with 15 new rows in our data set. And then the next step consists in using, so we have already learned all the relationship between the original x's, the original variables, manifest one. We have created higher level variables, so the factors, and the idea now is to learn again the relationship that hold between these higher level variables. So we are building a higher dimensional network, and we have again another ground network. And once we have that, we will connect the purchase intent to all these factors, and so we will do that manually, and then we will delete the connections that are not reliable. So we will use just the analysis of the strengths of the link in order to remove the weakest one. And then, so we have our probabilistic structural equation. So now we will be able to use this model in order to carry out analysis. And here we will just use this network in order to find what are the important drivers we can influence in order to improve the purchase intent of our perfume. So just by using BayesiaLab and the graph, we will be able to create automatically this quadrant where we have in the y-axis the importance of the driver, and in the x-axis the current mean value of these drivers. So this first quadrant is just based on the factors. So the new variable we have automatically created, And then we can do the same thing, but this time on the manifest variable. So, and a subset of these manifest variable, the attributes where we have the ability to impact on. Okay, and once we will have that, so we have built the network on the total market, and when we want to try to find an optimization policy in order to improve the purchase intent, we really need now to focus on one perfume. So if you remember well, when Stefan introduced the example, he said that the survey was based on monadic test, so one woman tests only one perfume, and then the idea here is to use the network we have learned on the total market and create one network for with the same structure, but with a parameter corresponding to the women who have evaluated the given perfume. And then we can have this quadrant, but this time this quadrant is focusing on product number 1. And then by hovering over a point, we will be able to see the level of the competitive product. And then we have an insight on the total market. And we are going to use this information in order to create a realistic optimization policy. And then we will be able to do target mean analysis. So as you can see, we have here a linear relationship and a highly nonlinear relationship, which is indeed the one, the intensity, the connection between intensity and purchase intent, which is what we call a just about right variable, meaning that if the perfume is too subtle, then it's not good. If it's too strong, it's not good. So there is a just about right level for this variable. And then, so the final step, which consists in using the network and our brand new target optimization tool in order to find what is the best policy in order to improve the purchase intent. So now that you have the main step in mind, I will directly dive into the BayesiaLab and do the demo. So I don't know if the image is in sync with the voice. So I will try to perhaps to go slowly. So here, I guess you can see the BayesiaLab screen, and so the very first step, as I said, will consist in opening the data sets where all the answers to the survey are. So we go to Data, Open Data Source, and this is a text file. So we can have connection with databases, but today we are just using a text file, a CSV file. So I'm just gonna open this perfume.csv, and this is the very first wizard for data importation. So we can use that in order to define if we want to discard or if we want to define new separators, what kind of encoding, if we have a title line, and so on. Define, sampling, but here it's not. We don't need to do that because we just have 1,321 data points. So we will just click on Next right now. This second wizard can be used in order to define, the type of the variable. So at the very beginning, BayesiaLab tried to guess what is the best type, and in green it means, or turquoise, it means that this variable can be considered as a continuous variable. And when it's red, it means that this is a discrete variable. And here, in our case, product is a kind of identifier. So we will not use it as a raw identifier, but we will use it as a discrete variable that we will use then when we will do our multi-quadrant analysis. Then we have the purchase intent. So this is the target variable indeed. And this is a 1 to 6 scale variable. And as we just have 6 states, we can also use it directly as a discrete variable. All the other one, fresh to radiant. So as Stefan said in the introduction, we have a set of variables corresponding to the perfume, and a second set of variables corresponding to the imagery of the perfume, of the woman wearing the perfume. So now these are 10-point scale, so from 1 to 10, and we are going to discretize this variable into 5 states by using, the equal distances algorithm. So this is just because our customer asked for that, so we have a bunch of other discretization algorithm based on decision trees, based on k-means, and so on. But here it's just one of the simplest one, so equal distances. So I can go directly there, and so for example, if I go into this distribution for fresh, I can see how it behaves. So we can see that these are integers, and I can generate a discretization into 5 states, equal distances, and then I have this. So we will set together 1 and 2, then it's 3, 4, then 5, 6, and so on. So instead of doing that variable per variable, I can also select all the continuous variable and then directly choose equal distances into 5 states. And then I click on Finish. And I have my very first Bayesian network. And as I said, we have, so if I just do that, we have 49 variables here, 1 per column, and we have these 2 variables that we will first exclude, because if you remember in the introduction, the very first step, or the second step after the imported data, is to find the relationships that hold between all these manifest variables, all these x's. So we will start by excluding these one, and we will use them in the other steps. And so just perhaps because Stefan did not mention any parameter in his introduction, so if I go there, so we have a second one where we can do inference with our network. I will just take randomly 2 nodes, and so I have the node for fresh, I have a node for rich, and then by double-clicking on these 2 nodes, I have what we call monitors. So 1 monitor per node. I can have 1 for all the nodes, but here I'm just focusing on these 2 ones, and that gives me indeed the marginal probability distribution of fresh. So for example, in this study, I had 9.69% of the women who said that fresh, with respect to the attribute fresh, it's lower than 1 or 2. Okay, and 25.66% rating this dimension with a rate higher than 8. Then we have the same thing for rich, and this is, yes, the global picture over the entire survey. And what we are going to do is we want to try to find relationship between these variables.
Sorry to interrupt. Could you zoom the validation window, please? It's not.
I'm sorry, I did not hear you well.
Could you zoom the validation window?
You want me to zoom? Yeah.
Yes.
Okay.
This would be good. Thank you.
So we have these monitors, and so in BayesiaLab, these monitors are really important because, as I said, the first thing, they gives you the marginal probability distribution of the variables, but it also allows you to do to use Bayesian network as a probabilistic expert system, and then send some kind of queries. So here I will not do that because I don't have any relationship, but we will do that later on. And in order to find the relationship between these variables, we are going to use information theory. So we will, for example, try to find is there any relationship between fresh and rich, and to measure this relation, instead of using statistical tool like g-test or chi-square or whatever, and then compute a p-value and then remove or add the links, we use this mutual information. And mutual information, just perhaps in a few words, so we have this marginal probability distribution for fresh, we have this one for rich, and then we compute what we call the entropy of each of these 2 dimensions. And the entropy is a measure that is the lowest value for the entropy is when I have this kind of distribution, so when I don't have any uncertainty, and this time entropy will be 0. And if I have a uniform distribution, so here with 20, 20, 20, 20, 25, sorry, no, 20, then we will have an entropy at the maximum level. Okay, and you can directly compute the entropy here by pressing I. We have the entropy for fresh in this example is 2.18, and the entropy for rich is 2.20. And now that I have a connection between these two variables, I can compute, the expected entropy of rich, for example, given that value, the value of fresh is lower than 2. So if I double-click in this state, I have a new probability distribution for rich, and then a new entropy, which is in this case 2.07. And I will compute all these new expected entropy for each state of fresh. And given these 5 new entropy, I will weight these 5 entropy by this probability distribution in order to compute the expected entropy given I know I have information on fresh. And when I'm subtracting this this original entropy, so the marginal one of rich, minus the expected entropy given that I know the value of fresh, then I have the mutual information. And so this will allow us, this is a key measure in BayesiaLab in order to find the relationship between the variables. So to tell the truth, we will not do that manually, arc by arc, but rather use automatic discovery algorithm. So we can go into learning, and then we will use the unsupervised structural learning algorithm and use EQ. So this will do all the tests for us directly, and at the end of the day you can see that we do not have any direct relationship between fresh and rich, but rather between fresh and flurry, fresh and correspond, and so on. So this is the final graph. Stefan said it was really something useful for communication, except when you have this kind of bag of nodes. So the idea is then to try to use layout algorithms. So we have a bunch of automatic layout algorithm in BayesiaLab, and the one we are usually using is the symmetric layout. And then I can, perhaps it will be short, but just okay. So now, I don't know if it's big enough to allow you to see the network, but we have all these relationships that have been automatically discovered. And so, but at this step, at this point, this is only a kind of qualitative results. We can see that high hand is connected to timeless, which is connected to classical, and then to is classical, but we don't have any idea of the strengths of these relations. So it's just a qualitative picture of the relationship. And to be able to have a kind of quantitative analysis of this network, we will again go into the validation mode, and we'll remove these monitors, and we will use a tool in order to analyze the strengths of each relation. So we can directly go to visual analysis, visual, and we will use the mapping. So it's another view of the Bayesian network, and I can directly use node force, for example, and Kullback Leibler here, and this way I have another view of the same network, but here the size of each node is directly proportional to the strength of this node in the representation of the joint probability distribution, and the thickness of the link is directly proportional to the strength of the relation between the variables. So we can see that even without focusing on purchase intent, right now we can directly see that we have really two really important dimensions. The first one is pleasure, and the other one is radiant, and then sensuality, metric attractive. And very intensity is not so important in this one, flurry, sweet, and so on. Okay, so now, as I said, one of the steps, once we have this ground network, we can analyze the strengths of this variable, and we will try to find, groups of variables that share common characteristics. So by analyzing the strengths of these links, we want to automatically cluster variables together. And to do so, we will go to analysis, clustering, sorry, and variable clustering. So this tool then, just as I said, is using the strengths of the connection, again based on information theory, and say that we need 15 clusters in order to have a compact representation of this joint priority distribution with higher level nodes. And I can click on the dendrogram, and I will have the resulting dendrogram. So it's a visualization of the clusters. And we can also use this tool in order to generate another view of this clustering. So this is, so we, by analyzing this ground network, this one, we were able to find automatically 15 clusters. So you can see this one, this pink node, is indeed the summary of these 4 nodes. Okay. And then we have these 2 nodes grouped together, and so on. So this is something you can change, because BayesiaLab just guessed 15 clusters by using powerful heuristic, but if you still are not agree with that, you can also directly change the number of clusters you want. You can use your knowledge of the domain. But in this demo, I will just use 15. And then once you are happy with this clustering, you can just validate, and you will be able to keep the colors. Just close that. And now, so we just have identified groups of variables, but it's just a qualitative identification. So we have defined factors. We have these factors here, and as we can see, we have factor 0 to factor 14, and the number of nodes associated to each factor. So again, if you have some expert knowledge, you can modify this, change, take one node, add it in the other class, and so on. So you can really use your knowledge in order to modify this clustering. And once we have all these classes, so the next step of the workflow will consist in creating one latent variable per group of nodes. So if I take this one, for example, we will create a new node that will summarize this 5 dimensions into only one. And for that, we go to learning, clustering, and we will use multiple clustering. So we have a bunch of options there, but I will not go into details right now. We will select between 2 and 5 clusters. It's OK, and then pressing OK. So now is learning, and so I will just close this. We have, so again, I will use the layout, automatic layout algorithm, symmetric. We have our purchase intent, we have our product variable, and for each identified cluster, we have a subnetwork indeed here. And before, using this directly, I will just focus on one of these subnetworks. I will take the first one, factor 0, and we are gonna analyze a little bit this network. So we can see that these variables were set together in the same cluster because they had some very strong connection. And then in the framework of Bayesian networks, this strong connection, we just grouping them, we think that there is a hidden cause that is indeed the explanation of this strong relationship between these manifest variables that perhaps are just measurement of the same concept. And so we are using, indeed, in order to induce this latent variable, we are using data clustering. So we are just having, in this case, we have 5 dimensions. So we have a joint priority distribution made of, which is indeed here a hypercube made of 5 dimensions. And the global idea of data clustering is to find a very compact representation of this hypercube in 5 dimensions by using only 1 dimension. And then, if I go into validation, we would just have a look to see what kind of node have been automatically created. So we can see that we have a new variable. So this variable is fully new. It was not included in the original data set, and it's a summary of these 5 variables. So we can see that we have discovered 5 states, and the very first one, C1, there is a 2.02 in between bracket here, meaning that this is, if I focus on women who were associated to C1, then we can expect to have a mean over these 5 manifest variables equal to 2.02. So, in other words, this means that in this C1 cluster, C1 group of women, we have women that are absolutely not agreeing with trust, bold, character, active, and fulfilled. They just set a note lower than 2, at least in average. So if I do that, now I'm using the model, I'm saying, okay, I'm focusing on this subgroup of women, C1, which correspond to 6.81% of the women, and then given this information, given this selection, I can see that indeed 83.33% of them have set a note lower than 2 for trust, the same thing, 92% for bold, and so on. So we have very weak rating for this 5 dimension. On the other hand, if I focus on C5, so without even double-clicking on this state, so without using BayesiaLab as an expert system, we can already know that this cluster corresponds to women who have set high rates for this 5 dimension, because the expected mean is 9.13. So if I focus here, we can see these high rates for these 5 dimensions. So another important point, so we have this, and we have created this variable, and we have also created new data in our data set. So in order to do so, we have read the data set. So for example, right now I'm reading woman number 0 in my survey, and this woman set a rate of 6 for trust, 6 for bold, 2 for fulfilled, 6 for active, and so on. And using this information with respect to woman 0, then I can use this model and compute the a posteriori probability distribution with respect to factor 0. And then the probability that she belongs to C3 is 82.33%, and probability she belongs to C4 is 17.65%. And then, by using the optimal decision rule, we will say that this woman belongs to C3. And we are going to do that for woman number 1, woman number 3, and so on. And then each one will be associated automatically to a new cluster in this factor 0 dimension. And this will be an additional column in our data set. Okay. So another important information is what are these percentages? So these are what we call the contribution. And so, as you can probably notice, the sum of all these percentages is 100. And in order to compute this, we indeed use what we call the direct effect. So, and perhaps just I will take 1 or 2 minutes here to speak about total effect versus direct effect. Let's suppose I'm just trying to measure the impact of trust on factor 0. So I will just focus on women who set a rate of 9, or who rate trust with 9. And given this information on this dimension, trust, I can see that I'm increasing the expected value of factor 0 by 2 points. Okay. So there is indeed a huge impact, because I increase by 2.7 for trust, and I have an impact of 2.2 for factor 0. But as you can see, we have also changed the distribution. So setting evidence on trust has also changed the probability distribution for bold, fulfill, active, and character. And then this is what we call the total effect, because we have introduced some information there, and this information has had an impact on factor 0, but also on bold, active, fulfill, and character. And now, when we want to use direct effect. So if we want to measure what is the impact of trust on factor 0, but without changing all the other variables, we can use what we call the direct effect. And the idea is just to select everything, all these monitors, fix their probability distribution, and then do the same thing. So I will double click on this state again. So I still have this plus 2.7 for trust, but now it's not 2.2 anymore for factor. It's 1.1, so it's half of this total impact. So, and now this is really what if I'm changing the perception for trust without changing anything else on the other dimension, and I can measure the direct contribution of trust on factor 0. Okay. So this is how we compute this contribution here, these percentages. And the idea, if you really want to see how it works, is just to do, where is my target mean analysis? I will use my shortcut, it will be faster. And so we can just display the sensibility graph. So this is the graph that shows you if I change the value of all my drivers, then I have the impact on my target. So this is trust. So if I decrease by 5 points trust, then I will decrease by 4.5 the value of my factor, my latent variable, which is called here trust underscore 5. And we can see that everything is almost linear. And so this is a total effect. So really the first example, if I set one evidence without fixing anything else. And now I want to do the direct effect analysis. So I'm just using this other tool, and I can see a slightly different relation now. So I have again trust, but this time is while holding fixed all the other distribution. And now we can see that everything now is not linear at all. We have these strange curves, and when we compute the contribution here, indeed we are focusing in this part in order to measure the kind of the slope here around the average value. So what if we are increasing a little bit the trust perception while holding fixed everything else? What will be the impact on factor 0? And here, so we can see that this represents 30% of the relation, and then 20% for full field and so on. So this is how we compute this contribution. So now we have seen how to build these factors for each dimension. We have seen how to create a new row, a new column for each latent variables that have been discovered. So now we have in this final network, we have these 15 new what we call flowers. So this kind of little networks. So where we have the let me just increase it a bit. We have for each new created variable, we have the variable plus the associated manifest variable, and also the contribution. Okay. And this is so the result of the multiple clustering. And then the next step will consist in, I will just remove this comment, will consist in trying to find now the relationships that hold between all these new variables. So the very first step consisted in learning the relationship between the manifest variable. Now we have created a higher level representation of these manifest variables, and we want to find relationship between these new variables. So we are going to use here again unsupervised learning and taboo. We just do 10 steps here and learn the relationships. And again, we still have our purchase intent on products that are excluded. I can use my shortcut for layouts, and I do have this final network. So as you can see, probably we still have our small connection between factors and manifest variable. We don't want to change that, and we have new relationship between the newly created variables. So this is now our ground network for level number 1, if you will, of our representation. And now, so the following step will consist in really introducing this dimension, which is our target variable. So I will define it as a target variable, and I will connect this node to the factors, because I have here it's how the system behaves, if you will, in this part, and here it's our target variable. So I'm just making a right click on this node and select connect classes factors. And now I have, so I make a connection with from my target to all the new x's we have created. So if you will, I'm just trying to create a formula y equal and a probabilistic relationship with all these newly created variables. And as I did that manually, now I just want to, in order to simplify a little bit this graph, I will analyze the strengths of these connections in order to identify what are the weakest ones, and in order to clean a little bit this graph. So I will go to analysis, report, and correlation with the, not correlation with target node. Here it's this one. So I have this report, and we can see that we have the g-test, which is modern version of the chi-square, and we have the p-value. And I will just select what are the relation I will have to delete. So let's suppose I will delete factor 12 because I have a p-value of 1%. I will delete factor 1, so let me just keep this here. And we are going to use our search tool with respect to arcs, and then I want to identify what are the connection with purchase intent, and in this one it will be factors. And I'm gonna select this one. So I want to select factor. I want to remove factor. Where are my values? Here. Bear with me 1 second. Here we are. So we want to remove the connection with factor 12, with factor 1, with factor 9, and we will also remove the last two ones, 6 and 11. Okay, and so we can sort this. So we want to remove 1, 12, 9, 6. Okay, I'm deleting these links, and now I only have significant relationships from my target to this ground network, and I can analyze a relationship with my target. So I'm gonna use for target correlation, and I can see that the most important relation with the purchase intent is factor 0. And then its pleasure correspond, and you probably can see with the colors that pleasure and correspond belong to factor 2. So this is indeed the manifest variable corresponding to these factors. So just perhaps in order to ease the analysis, I will exclude the manifest, and then we will do the same thing just on factors. So we have the most important dimension with respect to the higher level of the variable we have created. Is the first one is pleasures and sensualities and elegance and trends and high hand. And I can also directly generate quadrants for that to have another way to analyze these relations, and I can have the same thing. So we can see indeed that pleasure is the strongest relation with respect to purchase intent, sensuality, elegance, and so on. And we have the x-axis represents indeed the mean value, the current mean value of these latent variable over the total market. So this is something really useful in order to have an understanding of the domain. But this is not useful if we want to optimize one product, because if you remember, in this survey we have 12 products. So this graph corresponds to the relationship of over all these products. So now we want to focus on one given product, and we are gonna use this exact same structure, but we will estimate the parameter only on perfumes that have been on the women who have evaluated the perfume under investigation. So the very first step before doing that is to use the domain knowledge, the expert knowledge, in order to define what will be the drivers. So what will be the attribute we can have an impact on in order to change something on the perception of these attributes. So I'm just going to associate here a dictionary of cost. And then this dictionary, if you will, is, so the expert here told us that he will not be able to change anything in order to improve or change the value of bold. He will not be able to change anything on character, but he knows how to do something in order to have an impact on classical. The same for feminine, for flowery, and so on. But some dimensions are, yes, beyond his control. So this is just a subset of drivers that we will use for the optimization policy. So we have these drivers. We have defined our product, and I would just associate a class 2 for my non-confounders. And then I have this adject. Do you hear me well? Yeah? Is there any problem? No feedback? Okay, so I'm continuing. Assuming everything is working nicely.
Yes, it is.
It is? Okay. And then, so we have our network, and now I'm gonna use this, my product, in order to, create one network per perfume. So I'm selecting this and going to multi-quadrant analysis. I will use this product as a breakout variable. I will use the direct effect, rediscretize, that is. And okay. And now, so in this graph, this is my multi-quadrant analysis, and I'm focusing on product number 1, and I can see for product number 1 the most important dimension is fresh among all the drivers that have been selected by the experts. The second one is tenacious, then floweries and classicals and intensity and so on. And by hovering over one dimension like that, I can directly have the level of all the competitors. So we can see that for product number 2, the mean value for fresh is not so good, but it's not so important, and it's really not important for product number 6. I can do the same thing for tenacious. I can do the same thing for feminine, and then I will use this knowledge of the market in order to compute the gap to the best level. So from the right or from the left. So for example, for feminine, I will try to use this information to try to generate values between the rank of product number 3 and the one of product number 5. So I'm using this information in order to define the search domain in the space of the feminine dimension, for example. And the same thing here for classical. I will search between the product number 4 and product number 8. So using this information, I can export variation here, and I have my, not sure, say it correctly, yeah. And then by exporting the variation, I'm using the information on the competitors in order to be able to generate realistic optimization policy. And then I just have to go to my graph factor multi-quadrant number 1. So this is the same structure. Okay, exact same structure, but this time learn on the subset of women. So I should have something like 120 here, 120 samples. And again, I can do the same thing, make sort target correlation, and we can see that indeed the most important dimension is fresh. And then the second one is Flory, and so on. And we will use our brand new target optimization tool, and so we are gonna use here the variation we have created just before, import, and here, if you will, this is the mean value. So this is a current mean, for example, for classical, the current mean, or I will take fresh perhaps, as we can see it there. For fresh, as you can see, the current average for product number 1 is 6.4, and we know by using the multi-quadrant that we had the minimum value for one given product in the market was 3.37, and the maximum value was 6.87. So we will try all the combination from 3.3 to 6.8, and we'll see what is the best value here in this domain. And we'll do that for all these dimensions. So for wooded, the current value is 5.2. We will try from 11 to 0, because this is 0. We will not be able to increase the wooded value because wooded is has his highest value with our product, so we cannot improve it. So we'll just press OK, and then we are using our algorithm. So this algorithm is a genetic algorithm, so it's right now generating solutions, so it will take perhaps 30 seconds or so. But the important thing to know it's an anytime, what we call an anytime algorithm. So meaning that if you just let him work during 24 hours, he will just try to find the best solution during 24 hours. You can also define, heuristic stop criteria and so on. But yes, the idea is if you don't stop it, he will continue alone trying to find solution. So we can see that we are improving. So this is a way to see the solution, the evolution of the solutions. Right now we have a solution equal to 0.45, and just perhaps while waiting, so here we are generating solution on all these dimensions, so trying to find what are the best level, what are the best combination of these drivers that will allow us to improve the purchase intent while having something really realistic. So we'll probably just wait one additional generation here, let's say 10, and just to see what happened. Okay, so now this has created a set of solutions, and I will be able just to go to inference, interactive inference, and use this evidence scenario file to see what is the proposed optimization policy for product number 1. And we can see that this consists in increasing the fresh perception by 0.5, then increasing by 0.6 Flory, increasing by 0.7 personality, and so on. Increasing a little bit the intensity of the perfume, and so on. So, if you will, if we have 10 products, we will have to do that 10 times, and we will have for each product different result, different optimization results.